Already we have seen how to conduct experiment on level process and flow process. Today we are going to see how we can simulate a given system in a MATLAB environment. That we will see today. How to simulate modeling, tuning, and closed loop control of a soft process. Modeling, tuning, and closed loop control of a soft process. Soft process means here you will be given a transfer function 1 by s plus 1 to the power 4 or 1 by s plus 1 to the power 3, 1 by s plus 1 or 1 by s plus 5 to the power 6. Like that, a soft transfer function will be given. We have to control servo as well as regulate response for the given soft process. This will be done in MATLAB environment. Since it is a software experiment, we can do both type of tuning, reaction curve as well as sustained oscillation or continuous cycling method can be done here. Closed loop method also can be done here because it is software. That's why you can you need not bother about the time constant. In practice, we can do closed loop method only in fast process. That is in flow process only. The level, pressure, and temperature process, we have to go for reaction curve method. But here, since it is software method, that's why we can do both methods. That's why we are going to control. We have to tune the controller by using reaction curve method as well as continuous cycling method. That is the aim, to obtain tuning parameters of the given soft process by reaction curve method and then continuous cycling method, hence find the servo and regulatory responses. We know the formula for reaction curve method. The Kc for P only controller is Tp, time constant upon Kp, static gain multiplied by dead time. For Pi controller, the same value has to be multiplied by 0.9. Ti equal to 3.33 times dead time. For PID controller, this first value has to be multiplied by 1.2 times. Ti equal to 2 times dead time and Td equal to 0.5 times Td. This is for reaction curve method. For continuous cycling method, we will find the ultimate gain. That's why 50%, because gain margin is 2. That is assumed in Ziegler-Nichols method, 0.5 times Ku. For PI controller, 0.45 times. For PID controller, 0.6 times. Why here it is reduced than 0.5? Here why it is increased? That and all we will see in theory. Ti equal to Tu by 1.2. Ultimate period divided by 1.2 for PI controller. For PID controller, Tu upon 2, Tu upon 8. So these are the thumb rules suggested by Ziegler-Nichols. The procedure to obtain reaction curve here is, you cannot understand the instructions. That's why we will see in the MATLAB environment. Already we know if reaction curve is obtained, you know how to find the dead time. Dead time, how to find dead time? The point of inflection. The point of inflection, draw a tangent. Where it cuts up to that, it is dead time. So from that point to time taken to reach 63.2% of final value, we have to find the time. This dead time plus time constant time is T. So if you know the dead time, you can find TP. TP equal to T minus TD. KP equal to what? KP equal to change in output by change in input. Here, we are doing it from 0. That's why there is no nominal operating point. Since it is a linear process, you may not be understand, but since it is linear process, there is no problem in doing at 0 as well as at other operating points. So we are taking linear process. That's why the simulation can be done from 0. Sustained oscillation method, in that you'll note down Kc, for what value of Kc it exhibits sustained oscillation. Then we will measure Tu, ultimate period. Then we will apply the formula and find the tuning parameters. This is the MATLAB environment. Here you can write program. Like it is like C or C++. The instructions will be looking like C, C++. Not that much difficult, because the definitions it will be taken care by MATLAB. That's why you can use directly in this. The same C program you can run here. Any C programs can be run here. In this prompt you can run. But we are not going to work on this programming side. We are going to work on Simulink. Simulink is module-based programming. So the modules are available. Transfer function means the transfer function is as a module available. We'll pick and place and connect and we run. That is called a Simulink environment inside that MATLAB. So we are going to work on it. Simulink. For that, you have to select a blank model. This is the blank model that you have to select. You got one blank model. You have to save that. You have to give a name for that. Let us give soft process or fourth order. We are going to simulate fourth order process. So we selected the spreadsheet, a blank spreadsheet we selected. In that we will place the components. Components are already made by MATLAB. That will be pick and place. That's all. So we need a transfer function, or you can, if you know the name, you can type and automatically you will get. Transfer function. So the transfer function block is available. So we placed, or you can go in the library browser and you can select. There are also some search is available. You can search and find. If you know the exact name, no need to go here. You can type here itself. So first thing is we are going to get a transfer function. Transfer space FCN. That is the name of the function MATLAB used. That if you type, you will get. We placed. Or you can go here and in continuous sources, step function is available. So I want to take this. I can drag this. I can drag this and drop. So I can drag and drop. So we have to get step response. It will indicate whether you want to connect. So if you click that blue link, or you can connect like this. So now step input is given to the transfer function. We have to see, that's why we need a scope. Scope is required. Scope is required. So scope I got. Scope is placed here. The blue line is correct. That's why I'm just clicking, it is connected. So this is ready for reaction curve. But the transfer function given here may not be correct. It is given as 1 by s plus 1. So we have to get select the transfer function given is s plus 1 to the power 4. 1 by s plus 1 to the power 4. S plus 1 to the power 4. You cannot enter directly. We can enter polynomial coefficients. Polynomial coefficients can be entered. But here s plus 1 to the power 4. That's why we have to expand this. You know the triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 0 order, first order, second order, third order. So we have to find one more. 1, 4, 6, 4, 1. This is fourth order. 0 order, first order, second order, third order, fourth order. So this is the triangle to find the coefficients. So we have to enter these coefficients. So s plus 1 to the power 4 equal to s power 4 plus 4 s cube plus 6 s square plus 4s plus 1. So now we can enter this 14641. So we have to enter we have to enter denominator coefficients. Numerator coefficient is only one already it is there here. Now 1, 4, 6, 4 space between them we have to enter space s power 4, 4s cube plus 6s square plus 4s plus 1. 5 coefficients. That's all. So now we entered. If you want to see the transfer function, you can increase the size you will get. Are you able to see? S power 4 plus 4s cube plus 6s square plus 4s plus 1. Now we have to check whether the parameters are correct. The initial value is 0. For step input, how a step input looking like that? It will be looking like this. Initially it is 0, then suddenly it becomes 1. At t equal to 0, at t equal to 0, it becomes 1 and remains 1. That is step input. So to get a reaction curve, what we are doing in level process, the nominal value is 50%. We change it from nominal value to 55. 5% increase we gave. We gave a step change there to get the reaction curve. Same thing here we have to give. That's why step time is 0. Step time is 0. At what time we are giving? At when t equal to 0 we are giving. Initial value is 0. Final value is 1. So we are giving a unit step input is given. That's all. That's okay. So this is scope to see the response. This is the scope. That's all. So no response here. Now we have to run this. Run. That's all. You will get the response. But here it is not yet settled. Here it is not yet settled because the x-axis is up to only 10 seconds. It's not sufficient. So we'll increase that time. This is available here. Stop time. Stop time you increase to 20. You increase to 20. Then you run again. If you see that, so I got the reaction curve is applied. Reaction curve you can trace on a sheet, trace sheet. What is the name of the paper? Trace sheet. Okay. The trace sheet is available in the shop. It is wax coated paper. That's all. It is wax coated paper. One side wax will be coated. In that paper, you can a transparent paper wax coated. That's why it is. It can be used for tracing. So the trace paper, and that you have to trace this. Then you have to find what and all you have to find. You have to find dead time. So if you draw a tangent at the point of inflection, you will get a tangent will cut the x-axis here. Here you can find the dead time. Time taken to reach 63.2%. One means what is 63.2%? 0.63, 0.632. To see that we can okay, we can amplify this around 6. Okay. So you can find the value. You can amplify and see the value. Exact value can be seen here. About what is that? 6.3, 6.4, 6.35 here. So here about 4.36. 4.36. Total time is 4.36. Now we have to see the dead time. To see the dead time, you can see the dead time. Dead time, if you draw a tangent here, it will cut at 1.3. Let us see. 4.36 minus 1.3. Therefore, 3.036 is the time constant. Remember, 3.036 is the time constant. Dead time is 1.3 seconds. Gain is unity because where it settled finally? Where it settled? It settled at 1. What is the input given? 1. Input is, how much input is given? 1. Therefore, change in output by change in input, 1 by 1 equal to 1. Kp equal to 1. Therefore, the model of the process is G model. G of S is what? G of S is 1 by S plus 1 to the power 4. That is G of S. G M of S. Model is 1 gain. Time constant is 3.036 S plus 1. Dead time is 1.3 minus 1.3 S. That's all. This is the model of the process. Now we have to get the tuning parameters. Because we got the reaction curve. From the reaction curve, we got the model parameters of the process. These are the model parameters are TD equal to dead time equal to 1.3 seconds, time constant equal to 3.036, and Kp equal to 1. So now we can find the tuning parameters for P controller, PI controller, and PID controller. We have to find for Kc, we have to find for Ti, we have to find for Td. Small d is used for dead time, that's why let us put capital Td. Kc equal to what? Kc equal to, for proportional only, Kc equal to Tp upon Kp multiplied by Td. That is equal to Tp equal to what? 3.036. Kp equal to what? 1. Td equal to 1.3. Find the value. 2.33. Okay. 2.33. For proportional only controller, that's why there is no TA, no TD. What is for PI controller, what is KC? This must be multiplied by 0.9. So 0.9 times 2.33, how much? 2.09. Okay. PID, TD we have to find, TI we have to find. This is 2.09. You have to multiply this by 0.9 times. So TI equal to what? TI equal to 3.3 times dead time. Dead time is 1.3. Find 4.29. No TD for PI controller. For PID controller, we have to find the KC. KC equal to, we have to multiply this by 1.2. 2.33 multiplied by 1.2, how much? 2.79. This is 2 times 2.6. This is 0.5 times 0.65. That's all. So we got the tuning parameters. So now we have to simulate. So remember this, note down on a paper. I'll ask then and there. Proportional 2.33. PI controller is 2.09, 4.29. For PID controller, 2.79, 2.6 and 0.65. Noted? This part is over. Tuning part is over. That's why no need of this reaction curve. We can close that. Now we have to convert. This is in open loop. Input, output. That's all. Only open loop. Now we have to convert this into closed loop. So we are removing this and we are going to include a PID controller. PID controller. Yes, PID controller is available. That is included here. So here, this practical PID controller summing block is included, not in the soft PID controller. The practical summing block is inside. That's why you have to give set point and PV. It will subtract and it will find the error. But here it won't find the error. That's why we need a summing block. Summing block is available. So PID block is included. Now we have to give feedback. The feedback is given. Default is positive. Summing block both positive, plus. But we need negative feedback. That's why one sign has to be changed to minus. One sign has to be changed. Now it is negative feedback. That's all. Now we have to enter the tuning parameters. Now we have to enter the tuning parameters. Proportional default value is 1. Let us do for first P only controller. Proportional controller. What is the tuning parameter? 2.33. 2.33. Okay. Integral time Here you see the expression PID. The expression is Kc 1 by Ti is named as I. Kc multiplied by Td is named as D. That's why we have to enter I here. I means Kc by Ti. What is that Kc by Ti? But we are using only proportional only. That's why it is 0. If Kc equal to 0 for proportional control, Kc by Ti means you can enter 0 here. So we have to think and enter. If it is Ti means you cannot enter 0. Kc by Ti means you can enter 0. Kc by Ti we have to enter, that can be entered as 0. That's all. So we enter the tuning parameters. Now we have to simulate, that's all. So proportional only controller simulation we have to do. Run. We have step input. We have to see the response. The response is for 10 seconds only, but it is not yet settled. That's why let us make it 20. 20 is not settled. That's why let us make it 30. Yes, 30 almost settled. Almost. Not yet settled. This is the response. But where it is settled? It is settled about 7.75. Not at 1. Not at 1. What is the input here? What is the input here given? What is the set point? Set point is given as 1. Final value is 1. You can give 2 also. You can give 2 also. 2 is given. We run. We got the response. Where it is settled? Not 2. About 1.5 it is settled. About 1.5. You see that? Where it is settled? About 1.4 it is settled. But it is not settled at 2. Because we are using only proportional mode. If we include integral mode, then only steady state error will be removed. Already we studied in control system that if you use proportional only controller, there will be always steady state error. What is set point? Set point is given as 2. It should settle at 2, but it settled at 1.4 because it is proportional only controller. So proportional only controller always give steady state error. Steady state error. Not only here, in regulated response also it will give steady state error. Regulated response means no set point change. Final value is 0. 0 means it is at nominal operating point. It is at nominal operating point. 0 here in simulation, 0 indicates that it is at nominal operating point, say 50%. So it is at nominal operating point. We have to assume like that. We have to imagine like that. It is at 50%. Now, that's why I am giving final value also 0. It means that there is no set point change I am giving. I am going to do regulatory response. I have to give disturbance here. How we can give disturbance here? In level process, how we gave disturbance? Valve gives 50% flow rate. We changed that flow rate. Additional flow rate we gave, or we reduced the actual flow rate. In both ways we did. Here also we can give additional input, or we can reduce that. For that, to give the disturbance, I removed this link and I am going to include one more block, summing block here. I'm going to connect here. Additional input I am going to give here. For that, I need one more step input. So I copy that step and placed here. So I can copy any block, and like that I can copy the sum also. I didn't do that. So additional input is given here. This is plus sign only. You can put plus or minus. The additional input is again 0. Additional input is. Now let us give step time is 0. or step time I can give the disturbance at 5. Final value is 1. I'm giving a step input. A disturbance is given here at the 5th second. At the 5th second. Now we can simulate this. So disturbance is given. No set point change. It remains at 0. Up to 5, it is remains at up to 5. You notice that up to 5, it is remains at 0. That is nominal operating point. Say 50%. After that, disturbance is given. Additional input is given. That's why how much additional input is given? 1. So it should settle at 1. But where it is settled? At 0.4. So PID controller, P controller try to reduce, but it cannot remove complete disturbance. Because of P only mode. It is settled at 0.4. It should be at 0. We are expecting that it should be at 0. No disturbance affected the process. Like that, no disturbance should not affect the process. But it affected because of P only controller. If you use PI controller, this can be removed. Now, I want to know that this is what I did so far is qualitative analysis. It is not settled at 1.5. It is not settled at 2 for servo response. It is settled at 1.4. Then I gave disturbance. It is not completely rejecting, but rejected. Instead of settling at 1, it settled at 0.4. These and all what qualitative analysis. But I want to do the quantitative analysis. So I have to find ISE and IAE. To find that, I need integrator. So integrator means 1 by S. You know, 1 by S is integrator. So I have to integrate the error. I have to integrate the error, square of that error. Square of that ISE. To find ISE, what is the integral square of error? You have to continuously measure the error, square it and add, integrate. That is ISE, integral square error, to measure. So error is available. Here, the error is available after this summing block, error is available here. I will take that and I have to square that. To square, I can take a function, math function. Math function, and in math function, square is available. Magnitude square. Magnitude square, if I select, it becomes modulus of U square. So if you give error to this, I am giving error to this. Error is available here. That is given to that math function. So error is squared, then integrated. And we have to see the value. I need a display. Display block is available. In the display block, if I put, I'll get display block. That's all. So this is ISE I got. Integral square error I got. I want integral absolute error also. I want integral absolute error also. So what I have to do? I have to copy these 3 components required. So I am copying and pasting. That's all. So I got all these 3 components. I have to connect. That is here also I had to give error. Absolute function is available. Modulus of U is available. And then connect. That's all. Now it is IA is also available. Now if I run, you will get ISE IA. You got ISE IAE for what? For regulatory response. For regulatory response. For step response, if you want to see, then the final value made must be 0. So I made that final value 0. Initial value, both the initial value as well as final value is 0. Whatever may be the step time. Initial value is 0, final value is 0. No problem. So here step time is 0, initial value is 0, final value is 2. I want to give. For that, so this is IAE and ISC. We measured. If you have some other controller, for that also you can measure IAE, ISC, which gives less value of ISC, IAE is the better controller. Which gives lesser value is the better controller. Now, to compare two controllers, what we are going to do here is, we are going to use that sustained oscillation method. We are going to use the sustained oscillation method also, and we are going to simulate. Then we will compare two methods of tuning. We are going to compare two methods of tuning. We are going to compare. So now we will tune the same process by using sustained oscillation method. Sustained oscillation method means we need a closed loop. Closed loop is required, and we have to go on increase the and we have to put to P only mode. Already it is in P only. Already it is in P only mode. We have to give a step change. We have to give a step change of 2 is given, and we have to obtain the response here. So here the pole is in the left hand side. That's why it gives a stable response. Now let us increase this to 3 and run. So pole is approaching j omega axis. That's why oscillation is increased. It is not yet. Earlier it settled in 30 seconds. Now it is not yet settled. So the pole is approaching j omega axis. That's why oscillation is increasing. So let us give let us give 3.5. Now there will be a, what happens to the response? We see that oscillation further increases. Amplitude of oscillation further increases, but damped oscillation. Are you able to see? The amplitude go on decreases. Damped oscillation. But if you give or now you got sustained oscillation. Amplitude is constant. The poles are exactly on the j omega axis. Therefore, K max equal to 4. Note down. K max equal to 4. What is the period of oscillation? To see the period of oscillation, we have to amplify and see here. Period of oscillation. Here, the lowest value is 1, 3, 5, 4, 3. How many divisions? I couldn't see. So let us take this as 7.2. Starting value is 7.2. 7.22. Here, what is the value here? We'll see. The lowest value is 13.4. 13.2. 7.2. 13.2 minus 7.2, how much? 7. Sorry, 6. 6. 13 minus 7, 6. So 6 is the TU. TU equal to 6 seconds. We got two parameters. From that, we can find the tuning parameters. Find the tuning parameters for P controller. What is the tuning parameter for P controller by using continuous cycling method? For continuous cycling method, the tuning parameters are, for continuous cycling method, the tuning parameters are K max equal to what? K max equal to 4, TU equal to 6. So P only controller, for PI controller we have to find, for PID controller we have to find. Sundaramurthy sir on leave. So I am going to continue. So we have to find P, 0.5 times K max, 2. 0.5 times K max. 0.45 times K max. What is that? 0.45 times K max? 1.8, I think. Yes, 1.8. 0.6 times 2.4. This is 6 divided by 1 point, how much? 6 divided by 1.5. This is 3. This is 6 by 8, how much? 7.5. So we got the tuning parameters. You compare this with this 2.33, here 2. For P controller, how much you got? In 2.33, reaction curve method. Here 2. Ultimate gain is 4. Ultimate gain or K max is 4. Gain margin equal to 2 means 2 should come, which gives better calculation. Which method gives better calculation? Sustained oscillation method. Reaction curve method gives more approximate value. More approximate value only it gives. It is not giving 2 value. Depends upon, if you select dead time 1.3 we selected. If we select 1.2 or 1.1, it may give 2. So these are all approximate value only, it gives reaction curve. But the sustained oscillation method exactly give a gain margin of 2. 2 exactly it gives 2 because it is gives more accurate value. But no problem. It should not go to 4. If it goes to 4, it becomes unstable. 2.33 only, no problem. 2.33 only. That's why no problem. So for that, instead of 2.2, it gives 2.33 reaction curve. Here, 1.8, it's 2. That is also some 0.29 times higher, 0.29 times higher, 0.29 times higher, some 20% higher, 10% higher. Yes, 10% higher. 10%, 15% higher. So, no problem, because 4 is the ultimate gain. If you give 4, it becomes unstable. This, how much it gives? 2.4, reaction curve method, 2.7, 9. Similarly, for TI, it gives 5, here 4.29. Lesser value means higher value. 1 by TI, it gives higher value. Here, what it gives? 3, here 2.6. Here 0.75, it gives 0.65, lesser value. TD, it gives lesser value, but for other things, it gives higher value. Except TD, for other, it gives higher value. That's all. So both gives almost identical values. But which gives better response? Now we can see. Which gives better response? We can see. For proportional controller. For proportional controller, which gives better response? Now we can see. What is the tuning parameter here? 2. Now I need same thing again. I selected all. I copied. I paste here. I got one more setup. I got one more setup. One for reaction curve method, another one for continuous oscillation. So now I have to see both simultaneously. So I will take this and use a mux to combine these two together. So we'll select mux. I want to see both in the same window. So that's all. Now we have to enter tuning parameter here. We 2.33. Okay. Here it is 2. Now we have to simulate and see. What is the step response? What we gave? Step change of 2. So let us run. Which method gave? You see that for reaction curve method, the ISA is 20 because continuous oscillation method, the gain is 2. There 2.33, higher gain, definitely steady state error will be less. That's why that 20 only we got. Which controller is better? As far as IAE is concerned, reaction curve is better. Here 17, here 19. So see the response. Definitely the blue is continuous cycling method. Blue is continuous cycling method. How I am saying? Because here more error, here more error. Blue has more error, but less overshoot. Continuous cycling method, we reduce the gain. That's why overshoot is less. Overshoot is less. If you reduce gain, overshoot will reduce. At the same time, error will be more. Here you see that gap, integral of error. That's why error is more, but it quickly settles. Quickly, less gain, that's why it quickly settles. If you increase gain in a closed loop, zeta will increase. Zeta will increase. It is function of omega n. That's why you can analyze like this. But how many of you will analyze all these things, I do not know. But anyhow, with small response, we can think many things. Okay. So now you have to trace this P only controller. You compared both methods of tuning, you compared. Similarly, we have to compare. You trace this and write ISAE values. That's all. That part is over. This is what? Servo response. This is what? Servo response. Now let us do regulatory response. For regulatory response, no set point change. It remains at the nominal operating point. It remains at nominal operating point. That's why final value is 0 only. Here also the final value is 0 only. You can combine these two and give one step input. That is also possible. If you are going to give the same value means. So we are going to give same 0. Now we are going to give disturbance at time equal to 5. The final value is 1. Here also the final value is 1. That's all. So now we gave disturbance. We gave disturbance. For that, how it here which gives better response? Reaction curve gave better response. But reaction curve is not the better method. If continuous cycling method is there, then we should not go for reaction curve because the gain margin is 2, but it is not so. Gain margin is not 2. So it is not giving for our assumptions. So better response giving, that is different. But the stability is reduced. Relative stability is reduced, which is important. Relative stability is important. Gives better response, but relative stability is poor. So here we are going to compare which gives better response. That's all. So definitely, which gives better response? Reaction curve method gives better response. Here, yes. Which gives better response? Reaction curve method. That gives less steady state error. Deviation is less. Deviation is less. Yellow gives better response. So it should settle at 0. No deviation. No set point change is given. So it must be at remains at 0. Even disturbance comes, but it is not deviating to 0.4. If no controller is there, what will happen? If no controller is there, it will go to 1. It will go to 1 because of the disturbance. It will go to 1. Not in the screen. It will go to 1 because the gain of the system is 1. You are giving unit input. That's why the output will be 1. But because of that controller, it reduces to 0.5, 0.4, around 0.4. Sorry, 0.3, around 0.3 it reduces. Because of controller. Otherwise, no controller means the disturbance will bring the process to 1. Much deviation. So now let us check. You have to trace this regulatory response for P only controller. Regulatory response for P only controller. Now let us do PI controller. Here we have to enter tuning parameter of PI controller. For method of tuning is reaction curve method. What is the tuning parameter here? Reaction curve method you have to enter. PI value is 2.09 divided by 4.29. 2.09 divided by 4.29. How much? 0.48. Am I correct? 0.48. Okay. No derivative. Here, for this, for sustained oscillation method, proportional gain equal to 1.8. 0.36. So we entered the tuning parameters. First, let us do for load changes because already that value is entered there. That's why let us do for load changes. Let us simulate. Which gives better value? 2.77 here, 2.76. Continuous cycling method gives better response. For PI controller, continuous cycling method gives better response. Here, ISE, if you see, reaction curve method gives better response. It means, what is the meaning? Here, continuous cycling method, IAE is lesser. IAE is lesser. Reaction curve method, ISE is lesser. ISE is lesser. What is the meaning? What is the meaning? ISE will punish large error. IAE consider both errors equally. If you amplify 5, if you square 5, what you will get? 25. If you square 0.5, what you will get? 0.25. Ignore small errors. ISE ignore small errors. That's why you are getting lesser value. That's all. It punishes only large errors. But anyhow, IAE, if you see, it sees both error in the same point of view. That's why you got higher value. So it depends upon your requirement. You can consider either ISE or IAE. Now see the response. It is not yet settled. That's why let us increase this time to 50. Time to 50. Even at 50, it is not yet settled. So we'll make it, okay, anyhow, almost settled. Which gives better response? As far as overshoot is concerned, continuous cycling method is worst because it has a large overshoot. Reaction curve method, less overshoot. Which settles quickly? Continuous cycling method settles quickly. That's why it gives lesser IAE. But reaction curve method, large errors are here. Here it is not larger. That's why it gives lesser value. Error, largest number where you will get error. Here only you will get largest error. That is squared. That's why in ISE you are getting lesser value. The continuous cycling method is better. As far as overshoot is concerned, continuous cycling method is not better. Otherwise, quickly settles, no undershoot. You see that reaction curve method, large undershoot, but it has lesser undershoot for continuous cycling method. So this way you can compare. So we did regulatory response. That is the load response we finished. Now we will made the load 0. Load 0. Here also we will made the load equal to 0. Now we will test for servo response. Servo response. Final value is 2. Let us give 2. 2 or 1 depends upon the requirement you have to give. I am giving 2. Final value is 2. So now let us, which gives better response? Both ISE, IAE, continuous cycling method gives better response. You see here response. Continuous cycling method quickly settles. Blue line settles quickly. Already I told you that continuous cycling method gives better tuning parameters. That you can see in integral mode. Quickly settles. So both I value, TI value as well as KC are important. But if you see only proportional, it appears that reaction curve method is better. But if you do PI, it shows that continuous cycling method gives better. So if you tune better, response will be better. Tuning is how much important you can understand. Continuous cycling method only gives perfect tuning rules, tuning values. That's why it quickly settles. Even at 35 seconds, reaction curve method not yet settled. But here you see that at 30 seconds itself, even 25 seconds it settled, which is continuous cycling method settles. So continuous cycling method gives better. Even if you see the overshoot, continuous cycling method gives less overshoot. Less IAE, less ISE, quickly settles, less overshoot. What are the less IAE, less ISE, less overshoot, quickly settles. You have to trace this. Now let us go for PID control. Reaction curve method 2.76 or 7? 7.9. Okay. Integral time 2.79 divided by TI. How much? 0.08. Okay. Derivative time 0.79 multiplied by TD. How much? 4. 1.8. 1.81. Proportional 2.79 multiplied by 0.65. 1.8. So we entered for reaction curve. Similarly, we have to enter for continuous cycling. What is that? 2.4. 2.4. What is Kc by Ta? 2.4 divided by 5. 0.8. Okay. Derivative time 2.4 multiplied by 1.88. Okay. Now we entered. Already we did the servo response. Again, let us do the servo response. So we entered the tuning parameters. Let us do servo response. Settling time further reduced. Even within 2018, it is settled. Continuous cycling method, you see that where it is settled. Between 15 and 20, it is settled. So derivative mode reduces oscillation. But in practice, it may not happen because of noise. Noise will amplify the noise. Sometimes there is no noise. It is not stochastic process. It is deterministic simulation. Deterministic simulation means no noise is there. Not stochastic simulation. Stochastic simulation means practical situations will be included. It quickly settles, because of our D mode, it quickly settles. But the reaction curve method, large overshoot and all. So reaction curve method gives approximate tuning parameters. From that we can understand. You have to write the conclusion like this. Suppose you may got other ways because it is approximate for you while doing in the lab. You may get different values. Here we are using PI and PID. We forgot to notice one thing: no steady state error. You notice where it is settled. It is I mode is included. We gave 2. Set point, how much we gave? 2. Where it is settled? 2. No steady state error. For PI controller and PID controller, no steady state error. There also it is settled at 2. Here also it is settled at 2. But for proportional only controller, even we gave set point equal to 2, it is settled at 1.4 only. Steady state error were there. But here, for PI and PID controller, it exactly settles at 2. There is no steady state error. So these are the observations you have to write. So the final observation is the continuous cycling method gives better tuning parameter. That's why it gives better ISE, better IAE, less overshoot, quick settling time. Quick settling time than reaction curve method. That is the conclusion. You may get different conclusion. In the lab, you have to check and you have to write the conclusion finally. So now let us check the final part of this experiment is we have to do for regulatory response. Disturbance we have to give. Disturbance we have to give. For that, the final value of this is 0. And the final value of this set point is 0. It remains at nominal value. We have to give disturbance at 5 seconds. You can give at any time. Let us give disturbance at 5 seconds. 1 we are giving. Here also the final value is 1. That's all. Now let us simulate. Let us simulate. You notice that again, this as far as ISE is concerned, reaction curve method gives better because it punishes large errors. So, but it gives 0.3. You see the response, which has a large overshoot. Large overshoot. Continuous cycling method has large overshoot, but it quickly settles. So, if you don't want to have large overshoot for disturbance, then you should go for reaction curve method. Reaction curve method gives less overshoot, but large undershoot. Less overshoot, but large undershoot. He's here, bottom side. Undershoot is over, excess, but overshoot is less. But continuous cycling method, less undershoot, slightly higher overshoot. But if you consider IAE, settling time, continuous cycling method gives better response. It should not deviate from 0. It should be at 0. But because of disturbance, it goes up and finally the controller bring back to again 0. Controller bring back to 0. Instead of doing this way, you can do the disturbance by combining both. I am giving final value of 2 here. You can do both in single response. That is also possible. Where it settles, we noticed where it settles around 25, it settled. Am I correct? So let us give disturbance at 25. Instead of 5, we can give disturbance at 25. At 25, I gave disturbance. Here also, I am giving disturbance at 25 because at 25, it settled already. But the simulation time is not sufficient. That's why that will increase to 100. 100. That's all. 100. Let us simulate. Then only you can understand what is the meaning of regulatory response. What is the set point? 2. Set point is 2. Initially, it is at 0. The controller bring back to 2. Automatically, the controller bring back to bring the process to 2. Bring the process to 2. That too, you see which controller is better. Continuous cycling method is better because less overshoot, quickly settles. At 25, we gave disturbance. That's why this deviation. Otherwise, it remains like this. At 25, we gave disturbance. Continuous cycling method has slight overshoot, but undershoot is less for continuous cycling method. It settles around 50. Around 50, both settled. Around 50, both settled. I did both in single. Both in single. So here set point is 0. That's why it bring back to 0. Don't think that regulatory response will bring to 0. Don't think like that. The regulatory response will bring the process to set point. What is the set point now? 2. That's why it bring to the process variable bring to 2. I understand this point. So combined both together. Here you see that ISE, IAE, which gives better. In both cases, if we combine these together, continuous cycling method gives better response. We trace this and we will get.